Hi, good afternoon, everybody. My name is Joel Weber. This is Ray Cromwell and Stefan Haustein, my partners in crime over here. And we're going to talk a little bit this afternoon about HTML5. It seems to be a common theme in this conference. And specifically what you can do with HTML5 and the Google Web Toolkit. Little setup work. Just remember that there's a live wave going on. There's also a moderator question and answer there. And at the end of the talk, we'll get questions from both moderator and from the mics. So, we're going to talk about three things today. We're going to show you three things today. Something for your eyes, something for your ears, and something for your id. In other words, we're going to blow something up. You may have heard a thing or two about this. And specifically, we're going to talk about what you can do with Google Web Toolkit on top of HTML5. Obviously, HTML5 is its own technology, but there are some specific advantages that using GWT brings to actually doing HTML5 work to take advantage of these modern and bleeding edge browsers. So first off, I'm going to clear up a couple of things about HTML5 itself. We have a formal definition, that is the things that are actually in the spec called HTML5. Just best practices for HTML interpretation, some new elements, things like audio and video, so forth and so on. Then we have the thing that we actually are referring to most of the time when we say it colloquially, which include things like Canvas. Canvas may be part of the spec, I forget. But other specs like WebGL, WebSockets, all the stuff in CSS3, lots of little ancillary specs. And we've really been referring to it more in the colloquial sense as a whole in this conference because we believe that really captures the essence of what's sort of coming in the next phase of all these browsers that are busily updating themselves right now. So very briefly, you may be asking yourself if you're a current GWT user, well, where are all these great HTML5 features in GWT? And the answer is most of them are in extra libraries right now because we spend a lot of time trying to make GWT actually across browsers, so that if you write GWT code, it will actually compile and run everywhere within reason. We haven't moved these things into GWT proper for the most part, but there are a lot of internal and external open source libraries for wrapping features like WebGL and WebSockets and so forth and so on. And we're going to try to move these things into the core of GWT over time with appropriate measures to determine whether they're supported or not, so that you at least know what browsers you're actually going to be able to support. So first, WebGL. So all three of us are ex-graphics guys. Some game industry people, and when we saw WebGL, we thought, this is pretty cool. I had no idea when it was working on this. It turns out that there was someone at Mozilla, whose name I forgot now, but I will thank at the end for starting this work, originally called Canvas 3D. It's essentially OpenGL ES 2.0. If you're a graphics geek, you know what that means. It's the same OpenGL APIs you see on Android and the iPhone. And they've been made JavaScript friendly. So things that were sort of C-style APIs have been morphed into more JavaScript friendly APIs. Like I said, the work began at Mozilla, but it spread quickly into Safari and WebKit, and all three of them have I would say at this point, nearly production grade implementations. And it's the thing we all kind of hoped was coming when we saw canvas.getContext, and it took an argument that said 2D. The obvious implication of that is at some point we get 3D. It turned into WebGL rather than 3D, but the idea is the same. Little bit of a deep dive. Stefan's going to tell you a lot more about the details of the implementation, but the WebGL, if you're a graphics person, is kind of an interesting beast because it's really a drastic simplification of original GL libraries. Again, there won't be a pop quiz on these details, but it really moves a lot of the work into shader languages, and that's actually the really core thing that makes makes GL ES and therefore WebGL special. And that's really, really great for web browsers because the JavaScript VMs have gotten really fast, but they're not C code. C code has gotten really fast, but they're not specialized graphics processors. The more you can move over to these specialized graphics processors, the more really crazy heavyweight stuff you can do that would just have been completely intractable had you tried it in JavaScript or often even in just raw C code. So first, something for your eyes. I'm going to have Ray talk about a little library he built that does some things that I think are fairly interesting. And again, take this with, understand up front, these are sort of just bleeding edge demos. These are things, they're not finished products or anything like that, but they're there are attempts to really see what we can do with these new features in a fairly short period of time. So I'm going to pass it on to Ray now.
Thanks, Joel. So as Joel talked about, HTML5 has added a lot of new stuff, WebSockets, new elements, new APIs, but some of the most important APIs it's added has to do with media manipulation. So, I mean, it's one thing to use a video tag to just play back content, but it's another thing to use it to actually edit video. And some of the things that people used to do with Flash, because they could only be done with Flash or be done with a plugin, can now be done with HTML5. So what I've done is I've put together a little demo to kind of show what's possible. And the demo here basically is to try to recreate Photoshop filters in the browser, but to make them run really performant. So what we want to do is we want to make these filters work on megapixel images. So not just some kind of like small image you took with your cell phone, but 4 megapixels, 8 megapixels, and so on. So we want it to be really fast. Secondly, we want to provide it as like a general purpose library for GWT eventually, where if you want to build your own filters, you just kind of concatenate together a bunch of low-level operations like scaling, convolutions, transformations, and so on, and you can just make your own sort of Photoshop. But more importantly, we want to leverage native acceleration where possible. So if you've got a WebGL-enabled browser, we'd like to actually use the hardware to execute these operations. So this is just a sort of high-level overview of the architecture that I sort of implemented. It's basically a tree of filters, and each filter does something and passes it on to the next one. So, for example, the source filter, all it does is simply load the image from some resource, like a URL or off the disk and so on. And then you can basically send that into various other filters. One example would be like a color op, which could convert it to grayscale or sepia tone it or something like that. Another one would be a convolution filter, and convolution filters are really powerful. Many of the Photoshop filters use convolutions like sharpening and things like that, so you could do that. And you could blend them together, so you have separate layers, and you can do like Photoshop-like layers and blend them together and just output them to display at the end. So one of the things you might be asking is, well, what does GWT have to do with this, right? I mean, if it's JavaScript and WebGL in the browser, you could probably just write what I'm putting up here as the architecture in JavaScript, and that's true, you could. But what GWT buys you is two things. If you saw my compiler talk yesterday, it's able to optimize the JavaScript a lot more, so some of these really hot loops for processing pixels will run a little bit faster. Secondly, it allows us to target multiple platforms, which I'll get to. But anyway, there's two implementations. One of them is based off of just a canvas tag. And this new API where you're able to get something called a canvas pixel array and actually look at the raw pixels of a JPEG or a PNG that you loaded in. However, this mode's probably not going to be as fast as the hardware accelerated one. So for really large images, like 8 megapixel, we might have to like sort of crop it down and let you only kind of work on a preview image. And then the second implementation is WebGL. So if you've got a WebGL-enabled HTML5 browser, we're hoping that it's going to run blisteringly fast. So here's an example of one of the operations I'm going to show you. It's called a convolution. Now, what's a convolution? A convolution is simply a weighted sum of nearby pixels. So if you kind of think about you taking one pixel and then taking the ones that are right next to it and multiplying those by some value like 0.5 or 0.3 and adding them all together and then using that as the final output pixel. And the way this is represented typically is by a matrix. So up here is the 3x3 convolution filter. This is actually the sharpen filter. So if you're using iPhoto or Photoshop and you say sharpen this image, this is actually what it does. And what it's doing there is it's saying, look, take the current pixel you're operating on and multiply it by 5. Take the pixels to the left of it and to the right of it and above and below and multiply those by -1. Add them all together and output them. And you can make up your own convolution filters. You can plug in whatever your numbers you want to sort of play around in creating filters. But one important property is that if all the numbers add up to 1 at the end, it will preserve the overall brightness of the image. So that's an important property of convolutions. Some of the other convolutions you might be familiar with, Gaussian blur. If you've seen drop shadows or glow effects, that's how they do it. So we have a pure Java implementation written in GWT. And just to sort of give you a taste of the amount of processing that's going on in JavaScript, for a 5x5 convolution, as a 5x5 matrix, on a 1 megapixel image, you're going to do 25 million multiplies, adds, loads, and stores. Times 3, because you got to do it for red, green, and blue, and sometimes for the alpha channel. So that could be up to 100 million operations in JavaScript. And if your image is, let's say, twice as wide, it's 4 times as bad. So you can imagine it could get slow pretty quickly. Now, the WebGL implementation takes advantage of pixel shaders. So if you got WebGL, what we do is we upload a shader onto your graphics card, and the actual code executes on the chip itself. And if you're interested in actually how this is really done, there's a great article that NVIDIA has in their online book called GPU Gems. It's available at this link that will tell you precisely how to implement these filters on the hardware. But basically, it's really simple. If you know anything about graphics, you take the image that you want to process and you bind it to a texture. Then you just render a rectangle that's of a certain size, the size of the image. And you attach this pixel shader to it. So every time it tries to copy a pixel from the texture to the rectangles that's drawing it, it applies your code. It says, well, I need to write out a pixel, so I'm going to execute this little tiny mini program. And then finally, you just kind of run this in a loop if you want to apply a chained set of filters. So now I'll show you a demo. Well, okay. Hey, Joel, the backtick trick didn't work. Okay, I'll just switch over. Okay, so here is an image of Notre Dame. And what I do is I have a little sort of scaffold app here around my library. And I'm going to do some Photoshop filters on it. So the first set I'm going to show you is done in JavaScript. So for example, I'm going to click Gaussian, and I'm going to blur this image. So I'm going to click this button once, and you can see it's kind of frozen, the browser. And it took 1,600 milliseconds. That's like 1.6 seconds. I could click it again and keep making it blurrier and blurrier. Using a different convolution, you could do edge detection. Well, let me reset it. I combined a blur with an edge detection. That didn't. Okay, hold on. Let me reload it. Okay, let's do an edge detection. There you go. So that ran. Oh, that's the WebGL one. Sorry. that's why it's so fast. Here's the edge detection in JavaScript. 672 milliseconds. So there's another button I can click here, which is WebGL, and that's going to switch me over to hardware rendering mode. And if I click, I reload the browser. It's cached. So if I do it here, you can see I can click this, and I can just keep clicking it as fast as I want, and it just responds instantly. Like if I sharpen, I can sharpen it up. I can emboss it, and so on. Grayscale filter. And likewise, if I'm doing like color space correction, it's like real time. So if you're like editing the exposure of a photo, you want it to be like super real time. You don't want this want it to take like half a second every time you adjust. In fact, WebGL is so fast that we can actually play a video, and I can emboss Conan O'Brien in real time, or I can edge detect him. So if you haven't seen it, it's pretty funny. It's Vic and Conan together. So that's the gist of that demo. Let me go back to my presentation. Yeah, I keep forgetting where I am. Okay. So what have I shown you? What I've shown you actually is a library I've written in GWT called GWT for image processing for Google Web Toolkit. And what it is, it has 2 implementations. It's a pure Java implementation and a WebGL implementation. Now this is where the question of why GWT comes in, because you could do this with just pure JavaScript. And the reason is this. The pure Java implementation can actually run in the cloud. So if you wanted to do some image processing in the server, so offload it to the server, you could run this inside of App Engine if you wanted to. It's pure Java. Likewise, you could even port this to Android and just stick in the Android graphics APIs on the bottom layer, and it would work there too. But the front-end API would be the same. And it's got a compact DSL like API, so you just do something like imaging.load, a URL, .convolve, an array that has your kernel, and then .to and a widget to actually poke it into. An important fact, I've measured these WebGL filters up to 1,700 times faster than JavaScript. So if you want to edit really, really large images, doing it in JavaScript or doing it with like SVG filters is not going to fly. WebGL is the way to go. So now something for your ears. Can I see a show of hands? How many people in the audience have ever owned a Commodore 64? Wow. I didn't expect that. So if so, I think you might like this next demo. So we were trying to think about what kind of demos could we do that would kind of really freak you out. And I think this one's pretty freaky. So what we did is we ported a Commodore 64 emulator to JavaScript using GWT. And the demo I'm going to show you is not the full emulator. This is just the sound part. So what I've done is I've ported essentially the Commodore 64 emulator just to run a SID player for SID music. How many people know about SID music? OK. So what this is it's just basically it's a complete Commodore 64 emulator that only exists to play .SID files. So let me go there. OK. So I'll briefly play. Actually, this is not going to be Commando because I don't have the rights to it. It's a different song. But I'll click the link, and it's going to load up. Let it play for a second. OK, that's enough of that. So, Commodore 64 emulator in the browser. Let me go back to my slides so I can tell you what's special about it, besides the fact that Commodore 64 is cool. All right, hold on, Joel. I have to kill that. I think it was still playing.
Did you escape your way out?
I probably did. All right, it's going to go back to, yeah, OK, I'll just skip ahead. OK. OK, so what did we do here? This is a demonstration of HTML5 audio, but the current audio element can only play back just static sound files that you've got sitting on the web somewhere. So what this actually demonstrates is the fact that you can dynamically generate audio in the browser, but there's kind of a couple tricks you have to do. But the emulator, to do this, has to actually run a cycle-accurate Commodore 64. That means like 1,000,000 times a second. It's got to be executing the processor's opcodes. It's got to be fetching from simulated memory. It's got to be updating all the I/O chips. And actually, for the sound chip in particular, to make it sound authentic to an original Commodore 64, it actually emulates the hardware analog circuitry that was on the back end of the Commodore 64, so the capacitors and resistors and all that kind of stuff, to make it actually sound completely accurate. So it takes a lot of processing power, and the browsers are getting fast enough that they can finally do this. So just to keep in mind, SID music is not data. It's not like an MP3. It's not a codec. It's basically code. So the way you play the music is you have to run it. And the way this demo works is it basically 44,000 times a second, it samples these virtual I/O registers that are being emulated in the browser and then collects them into a buffer. And then what it does, it takes that buffer and it encodes it as an audio/wave, a PCM file, and then base64 encodes it into a data URI. And then finally inserts an audio source equals that URL, which is a long URL which has the entire sound clip in it. And it just keeps doing that as the song's playing.
Yet somehow it actually works.
Amazingly, yeah. So that's it for audio in the browser. And if people are interested in a deeper dive on this or how to do other sort of audio tricks, you can combine WebGL with audio processing. So you can do all kinds of cool things like having the hardware do echo and reverberation and things like that. But now I'd like to bring Joe up on the stage to give you what you've all been waiting for, which is blood and guts.
I suspect many of you have already seen this before, so it won't be a real pop in the demo, but still fun to see. So this also comes back to the question of why GWT. So what we've done, in case for those of you who are unaware of this, is to take the Quake 2 game from 1997, which still looks remarkably good for a 97 game, I must say. Taken a Java port of it called Jake 2 that someone wrote a few years ago. They sort of transliterated the code directly into Java to prove that Java could run this quite fast, which it actually does. And we saw this right about the time that WebGL started actually coming up with real implementations. We started seeing a real implementation in WebKit and Mozilla, or Firefox. we were kind of scratching our heads and thinking, well, could we really port that? Would that work? No, there's no way. There's no way that'll work. But, you know, why not, right? It's more fun than working on trying to optimize table rendering, so I don't see why not. So let's give it a shot. By the way, I wanted to make this a multiplayer demo, but as you've seen from both keynotes, wireless is incredibly unreliable, so we're just going to do this single player. Oops. Loading's a little slow, and I'll explain why later, specifically. Ah, there we go.
Establish communications. Priority alpha.
See if I can play this with a trackpad and survive. Notice I put it on easy for a reason. Also notice this is hitting about 22 frames a second on this laptop at 1024 by 768. Not as good as we'd like it to be, but it's not too bad. Ooh, I got that guy. That was beautiful. Come on, you know why they put the barrels there, right? They put them so you can blow things up. So you get the general idea. We've actually, this is just the demo levels. We've seen the full game run quite well. Actually, if I go that way, I'm going to get my button to give me in a big hurry. I happen to know from experience, so. And this is a very literal port. So we're talking about the direct code, all the logic's here. Multiplayer works like a champ. There's a guy hiding right there. Played this once or twice. And there's somebody hiding in there. He is. Nothing like having perfect foreknowledge of the universe to help you get through something. It's sort of like Groundhog Day with guns. And can I make it through here? All I really want is a shotgun. There we go. Okay, I'll stop boring with this any minute now, but I'm having fun, so.
You know you can't stop playing.
What time is it? 30? Okay, we have plenty of time. 37 minutes. Hey, this my last talk ran under by 20 minutes, so I'm not going through that again. Okay, let's see if we can make it through to the fun part. Guys with the big machine guns. And think about the fact we're talking about a browser right here. There we go. That's a much better weapon. This is a browser we're looking at here. I mean, imagine how cool it would be if I could just send you a link, and you click on it, and you're in a multiplayer game with me. I mean, this is a proof of concept. But you know, when you think about, there's a guy behind me. Oh, no head. That's not good. There we go. All right. So anyway, okay, I really am going to stop now. All right, I'm going to kill that guy, and then I'm going to stop. All right, all right. Oh, demo time. Apparently, that was demo time. Okay. So before I let Stefan's going to take an incredibly deep dive into all the details. He did a lot of the graphics work in this, and there was a fair amount of it. But to the question of why, again, why GWT? What is really valuable about having done this through Java as opposed to just writing this in raw JavaScript? Now, I might not be able to prove this statement, but I strongly believe that with the complexity of that code base, I think, what was it, 100,000?
100,000 lines of code.
Give or take, call it about 100K locks for you IBMers out there. That's a really complex code base. It's convoluted. It's good code by 90s era game standards. It's very clean code, but that's by 90s era game standards. It took an enormous amount of tooling to get through this process. And again, I'm going to let Stefan go into the details. But the tooling that we provided, the tooling that was provided by Eclipse, we primarily used Eclipse, although IntelliJ would be fine as well. Any tool that can provide lots of cross-referencing, lots of find me all the places where this piece of code is used, find me all the places where, transitively where this piece of code is used, tell me when I've made a mistake, show me a red squiggly in the browser when I have just screwed something up. It was a complicated enough porting process. Had we just, without having to worry about those kinds of problems, without the tools, I honestly don't think we would have ever completed it, because we're really talking about 20% time, really sort of negative 5% time project, the stuff that happens between 10 p.m. and midnight at home. So that's the reason this is GWT related, I would argue. And I have more to say about that later, but first let me let Stefan go into the excruciating technical details of what actually happened to make this go.
Thank you, Joe. Yeah, so when trying to do this port, we faced a set of problems. And the first problem was rendering. So the rendering API used in the Quake, original Quake source code, lightweight Java GL, is based on OpenGL 1.x. And it uses Java NIO buffers for data transfer. But WebGL is based on OpenGL ES 2.0, and you don't have any fixed function pipeline there, and it uses its own WebGL arrays and buffers. And arrays and buffers are distinct, and you don't have this distinction in pure Java. And of course, we didn't have any development mode support for WebGL in GWT. Then we had problems with resource loading. Because there's no file system in the browser, and the Quake code loads everything from the file system. And if we want to use XHRs for loading resources, they are asynchronous. So they don't really fit into the control flow of the existing code. And local storage is synchronous, but it has a very limited capacity. Then for networking, Quake uses UDP, but there's no UDP support in any browser in JavaScript. And some Java APIs the Quake code base is using are missing in GWT. And of course, we had didn't have any idea if it would be fast enough. Okay. So the first part is the render report. Our first idea was to just do our drop-in LWJGL emulation, and just to emulate the missing GL1.x fixed function pipeline. But the problem with that is that a pure drop-in wouldn't be able to take advantage of the DOM-based image loading capabilities of WebGL. And handling image data at the pixel level for transfer to WebGL in JavaScript seemed too expensive. And finally, we needed slightly different signatures to support WebGL buffers. I'll come back to this later. So instead of a pure drop-in replacement for LWJGL, we added an intermediate abstraction layer that is close to the original API and still uses NIO buffers. And the NIO buffers we emulate using WebGL arrays. And a nice property of the GWT development mode is that the NIO buffer emulation falls back to pure Java NIO in development mode. And that enabled us to create a wireframe renderer that we could use to debug in development mode without needing WebGL. So the whole structure of our implementation is that we have an abstract GL adapter at the top, and we have an LWJGL adapter that still runs the original code base, so we still can run it in Java, in pure Java on the desktop. And then our abstract GL 2.0 adapter does all the fixed function pipeline stuff, and that's used by the wireframe renderer and the WebGL adapter. And that's how the wireframe mode looks like. A trivial translation from GL1.x to WebGL is to turn all the calls, that's that vector data, into sequences of GL bind buffer, GL buffer data, and then GL vertex attrib pointer. To make this faster, we changed the code to make sure that static data, like level geometry, static line map coordinates, and stuff like that, is only copied to a buffer once and then reused. And in the code, we did this by assigning a unique ID to reuse buffers. So we can identify and skip the copy step for WebGL, but still run the original code in pure Java. We did some other rendering improvements for WebGL, basically to reduce the number of GL calls. We ported GL draw alias frame in mesh from draw elements to draw arrays. And we reuse part of the GL setup when rendering strings of text. The next problem was resource loading. Porting resource loading to asynchronous I/O. For textures, that was quite straightforward. We just deferred the corresponding GL calls to the onload event. And in the meantime, we use a holodeck texture. It looks like this. You have seen this while loading the game, I think. And that was quite straightforward and had little impact on the control flow of the game. The sizes of all images, which are needed in building the models, are sent to the client in JSON as part of index HTML. Porting the code for loading models and maps was a bit more difficult. As I said earlier, Quake assumes synchronous access to resources, so it required a significant amount of refactoring. The main trick there was to skip frames while resource loading is in progress. So for networking, we replaced UDP with WebSockets. And with the renderer, async I/O, and networking implemented, we were able to run multiplayer games. So ironically, multiplayer support was the easy part because we didn't need to port any of the server logic. However, we wanted to get the demo mode running. So we would have something that we could use as some kind of benchmark that we could reproduce, and that would like output some kind of frame rate, and then you see how good your browser or computer performs with WebGL. And after making sure that all the additional classes that were needed for this would compile, nothing worked for us. So we kind of knew that there must be an error somewhere in our changes, but diff showed that we had like changes everywhere, and that made it kind of hard to find the bugs. So instead of trying to fully understand what was going wrong, we just tried to reduce the differences. And that means we reverted all unnecessary changes in the code base, such as import cleanups, package changes, and formatting changes. And we also replaced other changes in the code. All changes where we could do emulations, we did so. So we added a simple file system simulation based on local storage for saving preferences and games. Before that, we were using a local storage directly for this stuff. We ported some additional parts of Java util, and we pushed down the networking changes from a pretty high level, where we were using JSON messages, to a low level, the net class in the code base, that's more at a byte level. So with those changes, we got the differences down, the files with differences down to about 60 from 200. And we also were able to reduce the amount of changes in the remaining classes. This didn't really provide much insight into the nature of the bugs we had in our code before, but it made them go away. And that's where I would like to hand back to Joel. Thank you.
So that was a pretty crazy process. Thankfully, Stefan is smarter than I am and was able to make it all work. I'm the one who made all those diffs that he had to revert. I came just hacking and slashing through it and then thinking, I'm sure it'll work out fine, or I'm sure I can debug it. Well, maybe not. But so we saw this. I mentioned a minute ago it was running 22, 23 frames a second on this laptop. This laptop is significantly faster than the machine you probably owned in 1997, and the frame rates are actually quite a bit lower. So this really begs a few questions. I mean, one, and to be fair, on my Linux desktop at home, which is rather beefy, it runs at about 60 frames a second, which is kind of nice. But still, it should be running at about 500 frames a second on that machine. I'm making up the number, but a lot faster. So this begs a few questions, like I said. One, is it the code? What could we do to the code to make it faster? Two, what could we do to the code and the compiler? That's because there is a compiler involved. What could we do to the browser to make it either just directly faster or change the APIs in such a way that we could make things run faster by using the APIs more intelligently or creating better APIs? And three, what does this tell us about the inherent limits of actually running JavaScript code? Inherent or near inherent. One assumes that V8 performance will eventually tap out to some maximum or some asymptote. And so, what's possible in JavaScript, and what would require you to switch over to something like native client. Now, as far as the code itself is concerned, this is two levels of porting across two different languages, effectively. I mean, certainly two different target platforms, and the code got pretty crufty in the process. There's a lot of things being done in code that would be better pushed off to the vertex shaders as well. So there's a lot of things that, there were no vertex shaders when this code was written. So things like, I mentioned mesh animation here. Mesh animation is done, Quake 2 did not use bone deformation. It used just keyframed point clouds and did linear interpolation between them. That's in straight up Java code and JavaScript ultimately, and that's really slow because it's essentially DSP style, floating point DSP style work being done in a language that was very much not designed for it. So we could move that over into the vertex shader and probably get a lot more performance out of that. A whole lot more, I'm sure. And we've seen that as a common hotspot because each one of those, even the little rotating things, are still running this deformation code, and certainly all the characters are. So there are a few other things like that, but those are essentially the bigger hotspots when you're running in the game. Good compiler optimizations. One of the goals also was, or at least for me personally, was discover things we could do in the compiler that we're not currently doing as well as we could. This is a big, complex app. So there's a lot of opportunity to learn from it. We discovered a couple of particular things that were nasty for this code that are a little unusual. One, it initializes lots of little bitty arrays, usually for major sees and verts, and that unfortunately incurs some overhead in the Quake compiled output right now that we aim to eliminate. Just some minor semantic fix-up between Java and JavaScript arrays, but we can get rid of that. I'm going to make Ray do that because he's a better compiler guy than me. Lazy static initializers are also a serious problem. So static initialization, when you hit a class for the first time, we do that lazily because that's the Java semantics. And because there are so many static methods in this code, you're triggering these static initializers everywhere. I've been pushing to eliminate those for a long time, even if we do break the Java semantics, just make it a -x optimization or something. That would make a pretty big difference. And at a complete guess, I would guess we could probably get 20% or so, at least, more speed out of those kinds of changes. Maybe more than that. I may be wrong about the mesh animation stuff. And if we were to completely rewrite the code rather than just porting what was there are probably a lot of other things where they're doing things that made sense in C that are probably have become awkward through translation. So that puts us let's say that puts us in the realm of 40% faster. There you're talking about something that's tractable. Like you could build a real game that way. You're not going to build Crysis 27 this way, but or Far Cry, whichever one's the engine and whichever one's the game. You're not going to be building that in the browser anytime soon using JavaScript. And probably you're not going to want to port your C game to JavaScript anyway. If you have a game written in C, you're probably going to want to use native client for that. It's a perfectly sensible thing to do. We just wanted to prove the bounds of where we could get to. So then it comes to questions of what do I do to make the browser itself faster. Now, the JavaScript engine could get faster, but there's probably some inherent limits there. I don't know what those limits are. You should probably ask the V8 guys what they think the limits are. But it's going to have, there's going to be some limits on that. One thing we really did find, though, because this is really probably one of the first big things built on top of WebGL, at least certainly that I'm aware of, and we really wanted to push on the APIs before they were solidified so that we could push back if there were things that needed to change. What we really discovered was, I mentioned earlier that loading was really slow. I mean, that map should have loaded, it was completely cached, it should have loaded in less than a second or two. I mean, there's a lot of stuff in there. You know, there's 2 megs of binary data or so for the level itself, plus the mesh animations and so forth take up some space. Parsing that binary data in JavaScript is excruciatingly slow. If you want to understand how slow it is, go try to write parse float in JavaScript from bits. It's exactly as bad as you might imagine. And we hit that thousands and thousands and thousands and thousands of times in the course of loading a level. Which begs the question, why are we even parsing floats in JavaScript? Why can't we just pass that data directly through to WebGL? And WebGL has these typed array classes, WebGL array, WebGL float array, et cetera, for this purpose, for loading data directly to the card efficiently. Problem is the gap's not covered between XML HTTP requests, WebSockets, and the WebGL layer. They don't speak the same language. So you end up having to parse all this data out in a really slow way in JavaScript through strings and then ultimately bit fields, and then repackage it in a form that WebGL wants. So it turns out that the guys at Mozilla and Kronos Group, who manages the WebGL spec, and on the Chrome team, were already thinking about this problem. We got together and we said, look, if you were to make the other APIs in the browser speak the same language, we could make processing binary data in the browser a lot faster. Some experiments yielded results of probably at least two, if not more, orders of magnitude faster. That also would have made Ray's life a lot easier with that audio example. I'm sure some of you cringed when he said, I packed it all into I PCM encoded it and then packed it all into a data URI, base64 encoded it and shoved it into the URL field. Like, that's just wrong. I mean, it's really cool that it works, but it's just wrong. So, but that's another perfect example of a place where if you just made all these APIs speak the same language, you can have huge optimizations that have nothing to do with making your code run faster and everything to do with not running code at all. So, you know, there are a few other things we discovered as well. In particular, that there is some inefficient frame buffer handling in Chrome right now that the team already knows about and is working on. So if you shrink that window down, the frame rate goes up pretty fast, which is kind of surprising given that it's not pushing the card very hard. So they're certainly aware of that, and they're going to work on that as well. But they already knew about it and are working on it. So the point, again, is let's see what we can do with HTML5, colloquial definition of HTML5, as it exists in modern browsers right now. That, to reiterate what we actually showed there, that demo was WebSockets, WebGL, audio, Ray showed the video tag earlier, local storage, right? Local storage for settings and preferences, things like that. And the canvas itself, obviously mixed 2D and 3D rendering. Anything else? I think that was it.
In HTML5, we probably used it.
Yeah, as Ray said, if it's in HTML5, we probably used it. And that was kind of the point. And, you know, again, this is not for necessarily, we're not suggesting that everyone should go porting their C games to JavaScript, but I think this is a pretty compelling demo of what you can actually get done now, completely ignoring the native stack. I mean, I think that is pretty impressive. And doing these kinds of demos will help us continue to get the APIs right so that we have proofs of concept before the APIs solidify, and we can really build the browser into a real platform. So, and I think you're probably aware of this, but the code it's all in an open source, it's all in a Google Code project, so you're welcome to download it and try it yourself. Obviously, we don't own Quake, so we can't just put up our own servers and let everyone play, but it's really easy. There's a couple of scripts to download and try it yourself, and get LAN multiplayer death matches going like it's 1997. So, a few thanks also, before I forget. id Software for being really, really awesome about open sourcing almost everything they do after it gets only slightly long in the tooth. Bitonic Software for doing the actual J2 port of of Quake and proving that it could actually be really fast in Java, and the Kronos group for maintaining and actually pushing this spec forward. Also, Vladimir, I will simply say Vladimir, if anyone has any idea how to pronounce his last name, please let me know. Thank you very much for getting this whole thing started. He's the guy at Mozilla who really kicked off this whole process. And Ray wants a special shout out for Lasse Orni of Covert BitOps, who actually provided the licensed Commodore 64 music. We really wanted to play the Commando theme, but we can't even find who owns it anymore. So
I think the proper Commodore 64 hacker term would be greets.
Greets too, yes, right. That would be the hacker term, greets to Lasse Orni. So thank you very much for providing that. And thank you all for sitting through this. We appreciate it. With any luck, feel free to come to the microphones if you have questions, and I'm going to try and cover the ones in the Dory, the moderator link as well. We'll do a little of both.
Hi. Hello.
Wow.
Is that image library posted somewhere?
I'm sorry?
The image from the first example, the image library, is that GWT library posted somewhere?
Oh, the image. Did you put that up on the?
No, it's not available yet because it's kind of in a wonky state. But as soon as it is in a nice state with some documentation, I will be releasing it. I'll probably announce it on GWT users or GWT contributors list.
Thanks.
Okay, yeah, and as soon as Ray gets a little post-IO sleep, he'll probably do that. And I'm going to go back and forth if it's okay between there and the. Wow, that's a lot of %20s. We will be promoting the use of GWT with WebGL as a game development platform. I think I've addressed that. This is an experiment more than it is an actual proposal for the way you should be doing things, but it's something to learn from. And yeah.
So I've certainly never, ported any, graphics games or anything like that. But I've created a couple libraries, Java libraries that are meant to be targeted both by Java-C and by the GWT compiler.
Right.
Rather than having two sets of code, I've sort of, gone through the strife of trying to make, one package that can sort of be used in either situation.
Right.
And I've done that a few times now, and I've started to see some of the abstractions that can be made. Anyway, so I'm just wondering if the GWT team at Google has started to notice similar abstractions, and if there's any effort or dream to come up with a set of standards for making libraries that are meant to be compiled by either Java-C or the GWT compiler.
Right. So, I mean, I wouldn't say as such in an overarching effort, but there are particular cases where, for example, we've run into problems with collections being inefficient when, maps and sets in particular being hyper inefficient when, fairly inefficient when translated to JavaScript. And we're trying to, for example, look at replacing some of those collections with lighter weight versions, for example, where that would work well on the server, but also are built with the constraints of JavaScript in mind. If there are other cases that you're hitting, I know that some cases where we're simply missing the string constructor that takes a byte array. Mostly because it's a giant pain to implement in JavaScript, and we ran into a bunch of those as well. But if there are specific cases that you've hit, and if you're noticing a pattern of cases you've hit where you had to do extra work to make the code work on both the server and the client, and assuming it wasn't things like thread that just aren't going to work, we probably should actually be accumulating that knowledge somewhere. So if you could bring it up on the contrib list, I'd really appreciate that. Actually, it'd be really helpful.
I think it's fair to say also that we've kind of been thinking a lot about code that runs in multiple contexts lately, and sort of ways that we can tweak the supersource mechanism to sort of generalize it more. And I think that's maybe in the future we'll have a better answer for the sort of hacky way it's done today.
Right, right. And that could actually really go a long way towards answering questions about not just server and client, but also say GWT client and Android client. So you can share code there as well. Here.
Cross-browser compatibility has always kind of been a paramount goal of web development that I've felt. What do you tell somebody with a bad GPU or a non-OpenGL 2.0 capable GPU that can do these GLSL and VBO things that you guys are putting onto a browser? Same thing video game vendors say, just, you're screwed or what?
I would say, and feel free to butt in if you guys have other thoughts. I mean, there's a serious problem, right? Especially on Windows platforms where you tend to have a pretty good DirectX driver and a really terrible OpenGL driver. Does anyone remember the name of the project that we open sourced recently?
The Angle project.
What was it?
The Angle project, A-N-G-L-E.
To port to
Oh, that's it,
DirectX
exactly.
natively.
Yeah, that's one opportunity. Someone's just really needed to sit down and write a good OpenGL on DirectX abstraction. It probably comes with some overhead, but it's a lot less overhead than not running at all. And you know, and this is sort of forward-looking, right? I mean, these are things these will be serious problems. People on bad GPUs, or people that only support, you know, the simplest kinds of shaders and things like that. So we view this as really forward-looking in that sense.
Is there any type of CPU fallback mechanism in WebGL? Or would it just be so unbearably slow it's not worth it?
It would probably be slow, so it wouldn't be worth the trouble.
I think for the
That's not
reason-
strictly true. There are some, but it would have to be at the driver level.
I think maybe what Kronos was getting at is because OpenGL was such an enormously large library, they kind of maybe went a little bit too far in stripping it down. But the idea was basically if they remove all of the old fixed function cruft, they could make the surface area of the API a lot smaller. So for like iPhones and mobile devices, it could be more compact. And the people who are partnered with Kronos basically are essentially voting on that spec, and they're saying, yeah, Apple's saying, yes, we will put a GPU capable of doing OpenGL, yes. And probably Android's team is saying, yes, we will do that. So that's probably how it arrived at that state where it's like, if you've got a DirectX 8 card on a Windows machine, you're probably out of luck. But we do have a canvas renderer, so if you want to go with flat shading, you can still play it. You just won't get textures.
Right. One other thing on that front is that if you look at where OpenGL is going, WebGL, OpenGL, you know, all the Android devices, all the iPhones, I believe the Palms as well, are supporting a baseline of GL ES 1.5 or 2.0, whichever it is. So that actually could, if that forces GPU manufacturers across the board to get into a mode where pretty much any device that you get, I mean, we're talking, you know, my little phone has a pretty good, you know, pretty solid driver on it. That could provide a pretty stable baseline, and that's a good enough baseline to do anything that we can do, for example. I mean, it's pretty much a similar level of functionality. So it's a little farther off in the future, I think, before the long tail of old GPUs goes away. But once we can get to that point, we'd have a pretty stable baseline for writing code across a wide range of devices. Sure.
Sort of 3 implementation questions. The first one, WebSockets is UTF-8 bound. Did you guys use BSON, B-S-O-N, for encoding?
Oh, you don't want to know what we used. I'm just kidding. Okay, I'll try not to dive too deep on this. We have 7 minutes, but very briefly, we cheated like crazy and used a custom encoding, which caused it to treat every byte as a separate entity. I found a few libraries that use this trick. You have to fix up anything that falls above hex FF something or other or something like this. So there's weird fix-up code you have to do, and this is precisely the kind of stuff that is precisely the reason that we wanted to move binary support directly into XHR and WebSocket and things like that. I mean, strings are just not always the right lowest common denominator. In fact, it was, even if you take something like JSON, we tried base64 encoding, that was even worse. Base64 coding was really, really slow, comparatively speaking. We're talking about 2 megs, you know, plus base64 overhead. That just takes forever to decode. And we even tried JSON encoding. The thing is, you're parsing an entire programming language when you do that. And it is, you know, you think of it as really fast in a browser because it's so much faster than anything you could write by hand. But it was, in my experiments, it was 250 times slower, almost precisely, than the equivalent just raw packed buffers passing them straight through. We kind of hacked up Chrome a little bit to do that. And so that's the reason to work around that, to do that. String encodings are the only option you have right now, though. You're absolutely correct about that.
And the second question was resource loading and mesh loading. You mentioned using JSON. Did you guys look into doing, say, loading a texture, binding it on a canvas, and then pulling it in, as rendering it with a vertex shader, like a height map field sort of thing?
Sorry, loading texture, I missed that.
Loading a texture and then using a vertex shader to adjust the mesh.
Oh, you mean for adjusting the the textures themselves, the gamma correction and that sort of thing?
A faster way to load the resource, the mesh resource.
Oh.
It's like decoding them, I think.
I'm not sure. That might have worked. It would be, you'd be paying for buffer copy backs from over the card. That probably is still faster than what we did. We should explore that. Actually, that might actually work.
Yeah.
It's kind of
our
a freakish hack, but it would be really cool if it worked.
Our first hacked up try was using like Canvas pixel array, and because there's Quake code where it's doing like, it's processing the images before it uploads them puts them in the image, and it's like doing gamma correction, all kinds of, like the light maps get all processed up, and
we ultimately dropped most of that, right?
Yeah, we dropped most of it.
The light maps are still processed by hand, I think. But anyway, I'll come back to that. But sorry, question.
When will GWT support the file API?
Support
file API.
Oh, file API. I think there is. So there's often a little misconception about what GWT sort of supports and doesn't. As I mentioned in the beginning, there are things that we have baked into the actual core jars that, again, heretofore we've always tried to make them cross-browser. But there are a lot of open source projects, and in fact, if you look up, go on Google Code, the regular project hosting site, search for GWT and HTML5, you'll find 2 or 3 libraries. They seem to be converging. Most of them are written by external people, but we're just eventually going to talk to them about bringing their code in that abstracts WebSockets, file API, local storage, WebGL, Canvas, et cetera. So, and they're solid. They seem to be, from what I've seen. So. Don't hesitate to look there for other sources of APIs. Again, we'll try to bring those in as fast as we can, but it definitely shouldn't stop you from using those. Let's see. When will GWT finally support Canvas? I think that's pretty clear. Unrelated.
Size question.
Oh, that's okay. So this question is about white paper describing the whole process. I guess we have a slide deck now. Stefan went into quite some detail on that. And SVG, MathML, et cetera. Again, look for third-party libraries. People, we're a fairly small team, and there are a lot of people out there doing a lot of good work faster than we can ever get around to it. So definitely look for open source projects when it comes to these things. And what will happen to Flash? There's a good question. I have no idea. Hopefully, it will continue to do very well as it's moving into Android and so forth.
On the size question, I think the compiled and gzipped Quake binary, the Quake binary is like, I think it's like 100K or something.
Gzipped maybe.
Yeah, gzipped. It's like 100K. So actually, it's not too large.
Right.
It's all of the art assets that are actually the largest part of it.
Right. Anyone else? Bueller? No? Okay. Well, thanks again, everybody. Appreciate your time. And take care.